Hey, let's get into some more calculations. All right, here we go. Calculate the solubility in molarity of solid calcium fluoride. There's my KSP. Okay. So first, it's useful to get a reaction for this thing so we can see what happened. So recall calcium fluoride looks like this. Calcium 2 plus, fluorine 1 minus. So this is a 1 to 2 solid like we just discussed in our shortcut. Okay. And so right away, if we're good at those kinds of shortcuts, then we should recognize this is going to become a 4s all cubed, where s is my solubility that I'm interested in calculating. Okay. And so now, because I have KSP and I want to find s, I just rearrange algebraically. So recall that goes as KSP divided by 4 all to the 1/3 power. So I got that by first dividing both sides by 4 and then taking both sides to the 1/3 power. Okay. So as you can see, once we know that shortcut, it does make the calculation go a lot faster. So let's do that. So that's going to be 4 times 10 to the minus 11. And so I want to divide that by 4 first. Then I want to take that to the 1/3 power. Okay. And so I get the molar solubility equals, so that's going to be 1, 2, 3, 4. So we'll say with 2 sig figs, 2.2 times 10 to the minus 4 molar. Okay. And remember, because we call this S, and because we call this 2s, that means with our stoichiometry, my calcium fluoride is the value of s. So that's why I'm just only solving for 1s. Okay. So now here's a slightly different problem. Calculate the solubility of solid calcium fluoride in a 0.025 molar solution of sodium fluoride. So we have a common ion effect going on here. And the first thing we should work out is what's going to happen to my solubility if I already have fluorine present. Okay, so it's a Le Chartier's principle, right? And here we can think of this in terms of a rice table if we need to, if that's going to help. And I'll chalk this up as a rice table just so we can see how this is going to go. All right. So we don't worry about any of these things initially. And now, of course, we recognize that our initial fluoride concentration, we were given a value for it. Let's see, where is it? 0.025 molar. And just like we normally do in our calculations, we'll assume that that's 0. So now, if we think about this in terms of a Le Chartier's principle, because we have an excess of fluoride, but we don't have any calcium present, that means some of our solid is going to want to dissolve to fill that in. However, we already have a large excess of this present. So what that means is we actually expect our solubility should be decreased, okay, via the Le Chartier's principle. So if I already have a bunch of this present, then that means I can't really get much more calcium to dissolve, okay? So, but if we weren't sure how to just rationalize that, we'll just follow our basic solubility calculation, okay? And or our basic rice table calculation, rather. So we know that this is 0, so that has to increase from x. So we know that then this would also have to increase by, of course, 2x. Okay. And so now that means this is just x, and now this means this is 0.025 plus 2x. I did it again. And now because my KSP value is really tiny, we're going to assume the value of x is small. So we're going to assume that this is basically equal to 0.0025. And now when I go to do that, so remember this is going to be KSP equals calcium 2 plus times F minus all squared. And so now that's just going to simply be 4.0 times 10 to the minus 11. I know I was using S and over here I was using X. It means the same thing. Apologies for the confusion. And so I could write this as X. And now, because I'm assuming the value of X is small compared to that initial fluoride concentration, we're just going to assume that that's roughly 0.025. And of course, I've got to square that. So now you can see here, to find the value of X, it's just going to be 4.0 times 10 to the minus 11, all divided by 0.025 squared. And let's do that calculation. So we've got 4 times 10 to the minus 11. And we'll say divided by 0.025 squared equals, okay, great. And I get now this value of X to equal 6.4 times 10 to the minus 8. So once again, we have to think about what that means. Well, if I go back to our original nomenclature, where this was S and this was 2S, that means this is S, and I get that just from the stoichiometry. Calcium is 1, fluorine is 2, calcium fluoride is 1. So we can see now the value of S is going to be the same as my value of X, which is my molar solubility. So in other words, now that means my molar solubility of calcium fluoride is 6.4 times 10 to the minus 8 molar. And we can see that that is much smaller than what it was before. And so if you think about this, what's happening with this common ion effect and Le Chartier's principle, because I already have such a large excess of fluoride, my solution can't really hold a whole lot of extra calcium fluoride because I already have such a large abundance of fluoride. And in fact, if we think about this, right, my value of X was 6.4 times 10 minus 8. If I wanted to calculate this, to be absolutely correct, it would technically be 0.025 plus 2 times 6.4 times 10 to the minus 8, which equals 0.025000128. So that means not a whole lot of calcium fluoride can be present with this large abundance of fluorine. Okay, so think about what that means in the common ion effect. If we already have a large abundance of one ion present, it's going to majorly decrease the solubility of our compound, of our precipitate. Okay. So I have one more sample calculation problem to do. This is a big one, so I'm going to make a fourth and final video for this learning goal.